Hello class, welcome to my screencast on the physics behind refractive errors in human eyes. These are errors that alter your eyesight, such as nearsightedness and farsightedness. Do you know why these things happen? It's got something to do with light, refraction, and different parts of your eye. But before we get into eye anatomy, let's talk about refraction and what it is. Refraction is the change in direction or bending of a light wave passing from one medium to another. Essentially, as light passes through a denser medium than air, the light wave passing through gets altered due to the change in wave speed. Here's the angle of incidence, and here's the angle of refraction. Now let's talk about eye anatomy. In this topic of light and optics, the cornea, the pupil, the lens, and the retina will be discussed, so it is important to know where these places are. There are four main types of refractive errors. The first one is myopia, or nearsightedness. This type of error occurs when the cornea is too curved, which causes the light rays to focus in front of the retina instead of on the retina. What happens next? Close objects appear clear, but far objects may appear more blurry. The second type of error is called hyperopia, or farsightedness. This occurs when the cornea is too flat and light rays focus behind the retina. This causes both close and distant objects to appear blurry. The third type of error is called astigmatism. Astigmatism occurs when the cornea is curved irregularly. When there are irregularities on the cornea, light gets refracted to more than one point at the retina. If you have astigmatism, light rays from lamps or traffic lights appear faded and its light rays spread out more. On the right is a diagram showing the spreading out of the light, and on the left is a normal lamp with normal eyesight. The fourth type of error is called presbyopia. This type of error happens as one grows older. How does this happen? Squinting. Squinting erodes parts of the cornea and manipulates its original shape. Thus, refraction is prone to occur when the cornea has many irregularities in shape. As it curves, it hardens, and close work or reading becomes difficult. Now, I will have some illustrations of normal vision, nearsightedness, and farsightedness. This is an illustration of normal human vision. The lines indicate light rays and the dotted line shows where the light rays reach. As the light rays reflect through the cornea, it is refracted and changes direction as it passes through the retina. A person with perfect eyesight would have all light rays directed at and on the retina. Next, we'll have nearsightedness. Again, the lines indicate the light rays, and the dotted lines indicate where the light rays reach. Light rays in nearsighted eyes converge before the retina. This is why far objects may seem blurry. Next, farsighted vision. Light rays appear beyond the retina, causing images to be blurry. The focus is actually behind the retina. So how do we fix these errors? There are four common ways to fix or alleviate the errors: prescription glasses, contact lenses, LASIK surgery, or to stop squinting to prevent future harm to your cornea. Now we shall review the two types of lenses. Recall that convex lenses are converging lenses, meaning that light rays join at the focus after refraction. As you can see, the light rays all focus into the focus, which is represented as that black dot. On the other hand, concave lenses are diverging lenses. The light rays move in repelling directions after refraction. Now let me draw the same two diagrams, but showing lines and the angle of refraction. In concave lenses, you can see the dotted line shows where the light rays are supposed to go, but then through refraction, the light rays are converging. To put all this into context, let me ask you, have you ever wondered how people can burn pieces of leaves with their magnifying glass? Well, magnifying glasses are composed of convex lenses. As light ray travels through the convex lens, the rays converge into a single point, and the image is reflected on the other side. This image is represented as the light beam, which can be used to burn leaves, ants, or even spiders. It focuses onto the focus, which is represented again with that black dot, or the ant that I'm drawing, or the spider. So what should a person with nearsightedness do? On the left, I am drawing a diagram before any alterations. Recall that the light rays approach before the retina. After the use of concave lenses, the rays are better directed towards the retina instead of right in front of it. The dotted lines show where the light rays appear to end. These lenses are available in glasses or contacts. For a more permanent solution, LASIK alters the shape of your cornea similar to the shape of the lens. So what should a person with farsightedness do? On the left is a farsighted eye without lenses. Recall that the light rays approach behind the retina. On the right, we can use convex lenses to better direct the rays to the retina instead of behind. Again, refraction is the key to manipulating the direction of the rays. Let's head on to some conceptual problems. A conceptual problem that can be asked through refraction is regarding a fisherman who is fishing for fish from above sea level. Right here I'm drawing a fish. I think that's a bit too far. I'm going to draw it a bit closer. Right there. Okay, so since light is moving through another substance, which is water in this case, the light rays get refracted. Therefore, fish appear further than they actually are. So where should he catch the fish or throw the bait? He should throw the bait closer to himself than where the fish actually appears for a more optimal fishing experience due to refraction. So throw bait closer to you than where it actually is. So let's get on to some math related problems related to refraction. Here we have Snell's law, which indicates that the product of the refraction index and the sine of the angle of incidence is equal to the product of the refraction index and the sine of the angle of refraction. Here the angle of refraction is represented by the letter n. The refraction index is essentially the value of how fast light travels through that certain material. Here's a light ray shown on a Cartesian plane. So here we have the x and y axes. We know that it's 90 degrees there. There's a light ray coming in from the third quadrant. For this, I'll have the index of refraction for water and for the first two quadrant. As it crosses the x-axis, it'll go through oil, which has a refraction index of 1.51. Here you see water 1.33 and it was 1.51. These values are usually given quizzes and tests. So the question actually gives you one of the angles. So the angle of refraction is actually 40 degrees. So in the first quadrant, I'm going to write 40 degrees. 40. So use Snell's law to compute the angle of incidence. Pause the video if you know how to do this, so figure it out by yourself first. So here you would plug in the known variables such as the refraction indexes of both substances and the angle of refraction that we know it's 40 degrees. So set it equal to each other, divide the right side by 1.33, which is the refraction index of water. I'll just type that into my TI-84. So 1.51 sine of 40 divided by 1.33, and then we would want to take the arc sine of this whole ratio right here on the right side. I'll just put that in my calculator.